The hidden silent shifts of the San Andreas Fault. Discovered by AI. There's a crack in the ground running through California that is longer than most countries. It has flattened cities. It has started fires that burned for days. It has killed thousands of people in a single morning. And for the last few years, this same crack has been keeping a secret. A secret so quiet that no person on Earth could see it. Even the smartest scientists staring right at the data missed it. That crack is called the San Andreas Fault. You have probably heard the name. It is the reason people in California talk about the big one, the massive earthquake that experts know will strike someday. But the story we're covering today is not the familiar tale you've heard before. In 2026, scientists finally observed the San Andreas Fault behaving in a way it was never thought to. It's a subtle, stealthy movement that has remained hidden for decades. This breakthrough discovery was only possible because scientists stopped relying on human observation alone and turned to artificial intelligence for analysis. What researchers found is deeply unsettling. The fault has been actively shifting, steadily sliding along its path, yet moving so slowly and gently that it produces zero ground shaking. There are no rumblings, no wall cracks, no detectable signs at all. If you'd been standing directly above the fault sipping a drink, you would have felt absolutely nothing. The ground beneath your feet crept forward silently, and humanity remained completely unaware. This is no fictional scenario or movie plot. It is a genuine geological phenomenon, one we are only just beginning to fully understand. The question is simple. How do you detect movement that is invisible, inaudible, and completely undetectable to human senses? For a very long time, this feat was considered impossible. Scientists suspected these subtle underground movements existed, but identifying them was akin to picking out a single whisper amid a stadium full of roaring crowds. These faint shifts were buried beneath endless geological noise, far too small and subtle to detect through traditional methods. For years, researchers had no viable way to uncover these hidden movements. That changed when a team of researchers adopted an innovative new approach. They input decades of underground geological monitoring data into an advanced computer program designed to identify minuscule patterns that human analysts consistently overlook. The AI system quickly uncovered a series of consistent, silent shifts along the fault. These subtle movements had been hiding in plain sight within years of collected data, undetected by human eyes until now. In total, the technology revealed dozens of these previously unknown hidden movements along the San Andreas Fault. While this discovery alone is groundbreaking, it is not the most concerning detail. What troubles scientists far more is the chain reaction that follows these silent fault slips. These subtle, unnoticeable shifts trigger subsequent geological activity that alters the fault's overall stability, and this pattern has researchers closely monitoring the region. We'll break down this entire phenomenon in simple, straightforward terms, free of complex scientific jargon. You'll learn exactly what silent earthquakes are, why they eluded detection for so long, how artificial intelligence finally uncovered their hidden activity, and what this means for the long-feared major earthquake looming over California after more than a century of buildup. By the end, you'll understand this geological risk far better than the general public, and you'll never view the seemingly solid ground beneath your feet the same way again. To fully grasp why these invisible, silent shifts are so significant, you first need to understand the true scale and nature of the San Andreas Fault, a geological giant far more complex and powerful than most people realize. To start, let's clarify what the San Andreas Fault truly is. Imagine Earth's outer surface not as a single solid shell, but a fractured layer of massive rocky plates, similar to a cracked eggshell. These tectonic plates are enormous, spanning entire oceans and continents. Crucially, they are not stationary. They drift slowly atop the hot, molten rock deep beneath Earth's surface, moving in varying directions. The boundaries where these plates collide and grind against one another form fault lines, and the San Andreas Fault is one of the most massive on the planet. Stretching roughly 750 miles across California, its length exceeds many state and national landmasses. This fault marks the boundary between two major tectonic plates: the Pacific Plate, which holds California's coastline and adjacent ocean floor, and the North American Plate, which forms the foundation of most of the North American continent. These plates do not collide head-on or pull apart from one another. Instead, they grind sideways past each other in a slow, constant, relentless motion. The speed of this movement surprises nearly everyone. The two plates shift past each other at just 2 inches per year, roughly the same rate human fingernails grow. This movement is so gradual that it is entirely unnoticeable in daily life, seeming completely harmless. Yet this slow, endless movement creates a dangerous geological trap. The two tectonic plates do not slide smoothly against each other in most areas. They lock tightly together, their rough rock surfaces interlocking and halting all visible movement. Even as the plates remain stuck, the constant pressure from deep underground continues to build unabated, year after year. You can visualize this tension by imagining bending a wooden ruler. As you apply steady pressure, the ruler curves and stores elastic tension, appearing stable and unchanging on the surface. But the tension continues to build until the ruler can no longer withstand the force, snapping violently in an instant. This sudden release of built-up pressure is exactly how earthquakes form. Decades of accumulated tension erupts in mere seconds of violent ground movement. The math behind this tension buildup is deeply alarming. 2 inches of annual movement may seem negligible, but when a section of the fault remains locked and immobile for a century, that incremental movement accumulates non-stop. Over 100 years, more than 16 feet of tectonic movement is pent up and trapped within the locked fault line. This is comparable to tightly winding a toy spring for decades and holding it in place with constant force, outwardly calm and stable, but holding massive latent energy that releases instantly the moment the hold breaks. Locked fault lines function exactly like this compressed spring. No one can predict the precise moment the tension will release, and when it does, the ground shifts violently. In a major earthquake, one side of the fault can lurch sideways by 10 feet or more in a single instant, a movement faster and farther than a human can react. This immense destructive power is why the San Andreas Fault is one of the most feared geological features in North America. This is not a theoretical risk. The fault has unleashed catastrophic earthquakes repeatedly throughout history, with devastating consequences that reshaped landscapes and destroyed human communities. In 1906, the northern section of the San Andreas Fault ruptured along a nearly 300-mile stretch in the early morning hours, catching residents completely off guard while most were asleep in their homes. San Francisco endured catastrophic structural collapse, with brick buildings, wooden residences, and commercial infrastructures crumbling to the ground in seconds. But the ground shaking was only the beginning of the disaster. Broken gas lines and overturned stoves sparked widespread fires across the city. With water pipelines shattered by the quake, emergency responders were unable to contain the blazes, which burned unchecked for days and destroyed vast swaths of the city. The disaster killed around 3,000 people and left more than half of San Francisco's population homeless, all unleashed in a single morning. Many historic neighborhoods were reduced to ash, and the city took decades to fully rebuild from the ruin. In 1857, the southern section of the fault ruptured across nearly 200 miles of land near modern-day Los Angeles. The earthquake was so powerful it left permanent, visible scars on the landscape that can still be seen from aerial views today. Rivers were displaced, and the ground shifted sideways by several feet, altering natural drainage patterns and creating new land formations overnight. The low local population at the time limited casualties, but a repeat of this earthquake in today's densely populated region, filled with millions of residents, sprawling highways, towering skyscrapers, and critical industrial facilities, would rank among the worst national disasters in U.S. history. Modern urban infrastructure is far more interconnected and vulnerable, meaning a single major rupture could trigger cascading failures across transportation, energy, water, and communication networks. More recent history proves the fault remains active and dangerous, with minor tremors serving as constant reminders of its latent power. In 1989, during a nationally televised major sports event, watched by tens of millions across the country, the San Andreas Fault shifted without warning. Live television feeds across the country captured the sudden shaking and signal distortion, bringing the raw power of the fault into living rooms nationwide. Within seconds, a double-decker highway in the Bay Area collapsed, the upper roadway crushing vehicles below, while a major bridge sustained catastrophic structural failure. The quake killed 63 people, injured hundreds more, and caused billions in economic losses. Yet this was a minor tremor compared to the long-anticipated major earthquake, merely a small release of accumulated tension from the fault's vast reservoir of stored energy. The southern segment of the fault that ruptured in 1857 has remained completely locked and silent for more than 165 years, making it the most high-risk section of the entire San Andreas system. Many ordinary residents assume long periods of geological quiet are a positive sign that the fault is stable and safe, but the opposite is true. Just like the bent wooden ruler, the longer the fault remains locked and stable on the surface, the more catastrophic tension builds beneath the ground. Fault lines do not release accumulated pressure passively. They store it indefinitely, stacking tectonic stress year after year with no outlet for relief. This centuries-long buildup of tension in the southern San Andreas Fault is the core reason scientists relentlessly warn about the looming major earthquake, commonly referred to as the Big One in public discourse. This is no myth or unfounded speculation. Comprehensive geological assessments conducted by the United States Geological Survey, USGS, and leading seismology institutions estimate a 75% chance of a powerful, destructive earthquake striking along California's fault lines within the next 30 years, with the San Andreas Fault's southern locked segment being the most likely source. Detailed computer simulations of a major Southern California earthquake paint a grim and concrete picture. Thousands of severe injuries, hundreds of fatalities, and hundreds of billions of dollars in direct and indirect economic damage. Post-quake fires mirroring the devastating 1906 disaster are expected to cause widespread secondary destruction, often inflicting more damage than the initial ground shaking due to broken utility lines and limited emergency response capabilities. For generations, this was the full scientific understanding of fault behavior. Faults lock, accumulate tension steadily over time, and release massive stored energy in violent, sudden earthquakes. This push, hold, and snap cycle was universally believed to be the unchanging fundamental rule governing the San Andreas Fault's activity, until the 2026 AI-assisted breakthrough that uncovered a critical missing piece of the geological puzzle. Researchers confirmed the fault possesses an entirely separate, previously unknown mode of movement that defies all traditional geological models and long-held scientific assumptions. And this secret, silent underground activity is exactly what advanced AI technology has finally unearthed after decades of invisibility. This new discovery completely upends our traditional understanding of earthquake formation and fault mechanics. For more than a century, seismologists operated under a single core belief. Fault lines only release built-up tectonic tension through violent, instantaneous ruptures that produce measurable ground shaking and surface damage. But modern AI-aided research has confirmed a second, entirely opposite form of fault movement. Instead of discharging decades of pent-up tension in a few catastrophic seconds of violent movement, the San Andreas Fault can gradually release small, incremental amounts of pressure over hours, days, or even weeks, with movement so gentle and gradual that it produces zero ground shaking, zero surface rumbling, and zero audible or visible signs of activity whatsoever. Scientists formally refer to this little-known geological phenomenon as a silent earthquake, or more technically, a slow slip event. At first glance, the concept of a shake-free earthquake seems contradictory and counterintuitive, like a thunderstorm without thunder or a wave without movement. Yet it is a fully verified, naturally occurring geological process, easy to visualize with simple, everyday comparisons that eliminate all scientific confusion. Imagine pushing a heavy couch across a wooden floor. A sudden, forceful shove creates a loud, jarring scrape, floor vibration, and abrupt, jolting movement. This is a perfect analogy for a traditional destructive earthquake. But a slow, steady, gentle push allows the couch to slide smoothly and quietly across the floor with no noise, no vibration, and no sudden jolt. This gradual, unnoticeable movement is exactly how a silent earthquake functions beneath California's surface. You can also picture a squeaky door hinge to further clarify the difference. Yanking the door open quickly creates a loud, sharp creak and immediate movement, disrupting the surrounding environment. But opening the door inch by inch over a full minute produces almost no sound or movement detectable to human senses at all. The door ultimately moves the exact same total distance in both scenarios, but the speed of movement entirely determines whether noise, vibration, and disruption occur. The San Andreas Fault operates by this exact principle during silent slip events, shifting its tectonic position steadily and imperceptibly without generating any detectable ground shaking or surface disruption. A natural and urgent question arises for both scientists and residents. If silent earthquakes gradually release built-up tectonic tension in a harmless, slow manner, shouldn't they reduce the overall risk of catastrophic major quakes in California? This is the most critical question surrounding the new discovery, and its answer holds one of the most surprising and unsettling twists of this entire geological breakthrough. Before unpacking the risk, we must first address the core challenge that stymied researchers for decades. How do you study, track, and analyze earthquakes that produce no shaking, no sound, and no visible surface disruption whatsoever? Traditional earthquake monitoring tools and seismograph systems are exclusively designed to detect ground tremors, seismic vibrations, and surface movement, rendering them completely useless for identifying silent, slow-slip events. These standard seismic sensors register zero activity, while the fault shifts quietly and gradually beneath them, leaving the entire category of silent geological movements completely unrecorded and unstudied for generations. To detect these invisible, undetectable geological events, scientists had to develop an entirely new category of high-precision underground monitoring technology, tailored specifically to measure rock deformation rather than seismic shaking. Researchers drilled hundreds of feet deep into stable bedrock across key fault zones and installed highly specialized geodetic sensors designed not to detect vibration, but to measure infinitesimal stretching, squeezing, and shifting of surrounding rock formations. These sensors possess almost unimaginable levels of sensitivity, capable of detecting the tiny gravitational and pressure shifts caused by distant ocean tides miles away. The sheer weight of incoming tidal water creates a minuscule gravitational pull on coastal landmasses, and these deep underground sensors can detect that faint force from miles away, an equivalent level of sensitivity to feeling a single feather land gently at the far end of a full football field. These instruments rank among the most precise scientific measurement tools ever created for geological research. A dense cluster of these ultra-sensitive sensors is installed in Parkfield, a remote, sparsely populated rural area in central California. Though unremarkable in appearance and largely unknown to the public, Parkfield hosts the most densely monitored, closely studied section of fault line on the entire planet. For more than half a century, scientists have saturated the area with hundreds of monitoring devices, transforming the quiet rural zone into a one-of-a-kind outdoor geological laboratory dedicated to studying San Andreas Fault activity. Researchers specifically chose Parkfield for a critical geological reason. Unlike the tightly locked, tension-building northern and southern segments of the fault, the Parkfield section creeps consistently with small, gradual, continuous movements instead of storing massive tension for catastrophic ruptures. This unique characteristic makes it the ideal global location to study slow, silent fault activity. We can visualize the entire 750-mile San Andreas Fault as a giant planet-scale zipper running across California's landscape. Some sections of the zipper glide smoothly and incrementally, opening slightly over time with no dramatic disruption or force release. These are the active creeping segments like Parkfield. Other sections of the zipper are completely jammed and locked solid, with zero visible or measurable surface movement occurring despite immense, unrelenting tectonic pressure building deep underground. These locked segments accumulate massive amounts of geological tension over decades and centuries, ultimately releasing all stored energy in violent, catastrophic ruptures that trigger major earthquakes. For decades, scientists held high hopes that by studying the predictable, active creeping section in Parkfield, they could unlock the hidden secrets of the dangerous, locked segments of the fault and improve earthquake prediction accuracy. But despite deploying the world's most sensitive equipment in the most closely monitored fault zone on Earth, human researchers still failed to detect the vast majority of silent slip events. Years and decades of accumulated high-precision monitoring data was filled with endless geological background noise, daily temperature fluctuations, seasonal tidal shifts, rainfall saturation, altering rock density, surface vegetation growth and decay, and minor atmospheric changes created constant tiny fluctuations in sensor readings. The faint, unique digital signature of silent earthquakes was completely obscured within this chaotic sea of data, entirely invisible to human analysts and traditional data analysis methods. Researchers knew theoretically that silent slips must be occurring along the fault, but they lacked any viable way to separate these subtle, meaningful geological movements from the endless stream of irrelevant background noise. This critical technological dead end is where artificial intelligence completely transformed global geological and seismic research. A team of leading seismologists and data scientists proposed a revolutionary solution. If human observers and traditional analytical tools could not distinguish silent slip patterns from messy, unstructured geological data, machine learning technology could be trained to do exactly that. Unlike standard computing systems that only follow rigid, pre-programmed rules, advanced AI machine learning programs are designed to identify subtle, recurring, non-obvious patterns hidden within overwhelming amounts of noisy, complex data, much like the human brain can effortlessly pick out a single familiar voice in a crowded, noisy room filled with hundreds of overlapping conversations. Researchers fed more than 40 years of continuous historical sensor data from Parkfield's comprehensive monitoring stations into the custom-built AI system, tasking it with scanning every data point to identify and catalog every silent slip event hidden within the decades of unanalyzed records. The AI systematically sorted through billions of data entries, intelligently filtering out irrelevant noise from tides, weather patterns, surface environmental changes, and instrumental drift to isolate the unique, gradual, consistent pattern of silent fault movement. The final results were unprecedented and reshaped the entire field of seismology. The AI successfully uncovered nearly 90 distinct silent slip events along the Parkfield fault segment, more than 20 of which had been completely missed by decades of rigorous manual human analysis by top geological experts. These hidden geological events had been clearly recorded in plain sensor data the entire time, yet human observers lacked the precision, patience, and pattern recognition ability to detect them. This landmark discovery proves silent earthquakes are not rare, anomalous, or one-off geological events as previously suspected. They are frequent, regular, ongoing occurrences along the entire San Andreas Fault system, happening constantly in the background, far beneath human awareness and detection. To eliminate any doubt and fully validate the AI's findings, scientists cross-referenced every detected silent slip event with data from completely independent monitoring instruments and satellite geodetic systems. Separate sensor networks and satellite tracking recorded identical subtle rock movements at the exact same timestamps, confirming the events were genuine geological activity, not computer errors, data glitches, or analytical anomalies. The truly unsettling revelation emerging from this research is not just that these silent slips exist in abundance, but the consistent, predictable geological chain reaction that follows every single event detected by the AI. After every confirmed silent slip, researchers observed a measurable, statistically significant increase in tiny, deep underground microquakes across adjacent fault zones. These microquakes are far too faint and deep to be detected by human senses or standard seismometers, but their consistent timing and spatial distribution reveal a critical, previously unknown connection between silent slips and fault stability. This consistent pattern definitively confirms that silent slips are not passive, harmless events with no lasting geological impact. Each subtle, invisible shift redistributes underground tectonic pressure and alters the stress balance of adjacent fault sections, creating minor but meaningful perturbations in the locked, tension-heavy segments of the San Andreas Fault. The subsequent cluster of microquakes serves as tangible proof that these invisible underground movements actively interact with and disrupt the fault's overall tension equilibrium, slowly altering its long-term stability. We can visualize this subtle but dangerous risk with a simple, intuitive, everyday analogy. Imagine a glass filled completely to the brim with water, held perfectly stable by surface tension despite being technically overfilled. The glass appears completely calm, still, and stable to the naked eye, but it exists on a razor-thin margin of physical balance. The slightest tiny bump, vibration, or air disturbance will break the equilibrium and send water spilling over the edge. The locked, tension-packed segments of the San Andreas Fault are identical to this overfilled glass. Outwardly stable, quiet, and motionless for decades, they hold centuries of pent-up tectonic pressure, existing perpetually on the brink of a major catastrophic rupture. Silent slips occurring in adjacent creeping fault sections act exactly like that tiny, disruptive bump to the overbalanced glass. Most minor pressure perturbations do not trigger an immediate catastrophic rupture, but the longer a locked fault segment remains stagnant and overloaded with accumulated tension, the less external force is required to tip it into failure and trigger a major earthquake. This is the core critical concern driving ongoing scientific research. Can recurring, frequent silent slips incrementally destabilize overpressured, locked fault segments over time and ultimately trigger the long-anticipated major earthquake that threatens California? It is essential to clarify key factual context to avoid unfounded public panic and misinformation. Scientists have not confirmed that silent slips directly cause major earthquakes, nor do these new discoveries signal an imminent earthquake or impending disaster. Silent earthquakes have occurred naturally throughout the entire geological history of the San Andreas Fault, and major catastrophic ruptures remain rare, low-probability events in any given year. The vast majority of silent slip events produce no dramatic geological consequences and do not immediately threaten human communities. What this discovery fundamentally changes is our century-old understanding of core fault mechanics. For more than a century, the entire field of seismology operated under a simple two-state model for fault activity, locked and stable, or actively rupturing in violent earthquakes. We now definitively know the San Andreas Fault is constantly, actively moving beneath our feet with countless subtle, hidden movements that continuously reshape underground tension dynamics and alter fault stability. These previously invisible geological processes fill massive critical gaps in our centuries-old understanding of earthquake formation and fault behavior. Every hidden silent slip event we uncover adds a new vital piece to the centuries-old puzzle of earthquake prediction and risk assessment. While we still cannot forecast the exact timing, location, or magnitude of individual major earthquakes, this AI-powered monitoring technology gives scientists an unprecedented, revolutionary new tool to observe, measure, and understand the planet's most dangerous fault lines in real time. This breakthrough is actively revolutionizing modern seismic research, turning previously undetectable geological activity into measurable, analyzable data. With this new technical understanding, it is reasonable for residents and observers to question whether this discovery creates immediate cause for alarm. The most pervasive and persistent myth surrounding California earthquakes must be dispelled outright. The idea that California will split off from the mainland and sink into the ocean during a major earthquake is purely fictional Hollywood lore, with no basis in geological science. The San Andreas Fault's tectonic plates slide horizontally sideways past one another. They do not pull apart, create open chasms, or trigger landmass submergence. Over millions of years of gradual tectonic movement, California's western coastline will slowly drift northward by a few inches each year, but no catastrophic sinking or continental separation will ever occur. Crucially, the discovery of silent slips does not predict an impending major earthquake or signal that the big one is imminent. Scientists still cannot pinpoint exact earthquake timelines, and this research does not raise the immediate short-term risk of a catastrophic rupture. This breakthrough is not a disaster warning. It is a transformative advancement in monitoring technology that drastically improves our ability to observe, understand, and predict fault behavior, ultimately making California communities safer through improved risk modeling and emergency planning. The difference between a catastrophic, life-altering disaster and a survivable, manageable seismic event is never random luck. It is almost entirely determined by proactive preparedness and infrastructure resilience. For decades, California has invested billions of dollars and decades of rigorous research into seismic resilience and disaster mitigation, reinforcing aging bridges and highway overpasses, upgrading public and private infrastructure, strengthening school and hospital buildings, and implementing some of the strictest modern building codes in the world, all specifically designed to withstand intense seismic shaking and minimize structural failure. A comprehensive statewide West Coast earthquake early warning system is now fully operational, providing critical advance alerts to government agencies, emergency services, businesses, and residents. Since destructive seismic waves travel far slower than electronic digital warning signals, the system can deliver anywhere from several seconds to nearly a full minute of advance notice before dangerous shaking arrives at any location. These seemingly short windows of warning are genuinely life-saving. The advance alerts allow public transit systems to slow and secure trains to prevent derailments, fire stations to pre-open bay doors to avoid jams during shaking, hospitals to pause critical medical procedures, elevators to land safely at the nearest floor, and residents to execute drop, cover, and hold-on safety protocols before the worst shaking begins. Countless emergency preparations that would be impossible mid-disaster can be completed in these precious few seconds, drastically reducing injury, fatality, and property damage risks. This groundbreaking research reinforces a vital public safety takeaway. Living near any active fault line demands consistent, basic preparedness, not constant fear or anxiety. Simple, proactive household and community steps, assembling 72-hour emergency supply kits with food, water, and medical supplies, securing heavy furniture and appliances to prevent falling hazards, mapping safe evacuation routes, and knowing basic disaster response protocols drastically improve survival and recovery outcomes during seismic events. These small, low-effort preparations require minimal time and cost, but make an immeasurable difference during a crisis. Beyond public safety and risk mitigation, this discovery is ultimately a powerful testament to human scientific progress and technological innovation. For more than a century, the San Andreas Fault's silent, slow underground movements remained a closely guarded planetary secret, completely undetectable to human observation and traditional scientific tools. Through the combination of ultra-precise sensor technology and cutting-edge artificial intelligence analysis, we have developed the ability to perceive the planet's most subtle, invisible geological activity, natural phenomena that were once entirely hidden from human understanding. Crucially, this breakthrough is not limited exclusively to California's San Andreas Fault. The same AI-driven data analysis framework can be universally applied to fault systems and seismic zones worldwide, unlocking countless hidden geological patterns buried in decades of unprocessed, unanalyzed global monitoring data. Silent, slow-slip events may be occurring constantly beneath major populated cities across every continent, completely undetected until now. For 100 years, scientists believed we fully understood the fundamental mechanics of earthquakes and fault behavior. Today, we are humbly discovering how much hidden, dynamic activity occurs constantly beneath our feet. And for the first time in human history, we possess the technology to uncover these long-buried planetary secrets and protect human communities from ancient geological risks.